Okay, so and you guys are familiar with how to calculate them and their limitations and all that good stuff, right?
Sure.
Good. Okay, so let's talk a little bit more about electron configuration. It's often called the electron structure. So electron configuration just basically lets us know where the electrons are going to be most likely, and we know that that's going to be based upon energy, right? Because it's all going to be based upon energy. And we know that the principal quantum number represents that energy level, or it also represents the orbital size as well, in a sense, because we know that the ones that are in those outer shells are going to be bigger, right? Okay, so so the further we get out, right, from the nucleus, the weaker it's going to be. The weaker the attraction is going to be. Does that make sense?
Yeah, that's like if you pull your magnetic pieces apart, the bond isn't as strong because of the distance, right?
That is correct. That is exactly it. Yep. Okay. So okay, so when we talk about energy levels as well, we know that the S is less than the P, it's less than the D, and that's less than the F, right? And so when we typically fill our energy levels, we fill our S, our P, then we get to our D later on, and then F. And again, the electrons are thinking less energy as possible, so they're always going to fill those lower energy levels first, and then they're going to work their way up to those upper energy levels. Okay, so let's give this a shot. So this is basically an energy diagram for just a general energy diagram. So let's do carbon. So how many electrons does carbon have?
6.
Okay, so carbon has 6 electrons. So if we draw the electrons for carbon, let me find my pen. Can you guys see my screen?
Yeah.
And
it's big.
It's big. Okay, good.
It's big.
Okay, so we start here. This represents the first electron. That represents up, means that it's going in like the positive direction in terms of the spin. This guy would be going in the opposite, the negative direction. So that's negative a half. That's 1, 2. We'd fill the 1s first. We then fill the 2s. And then we'd have 2 that are in the 2p.
I have a question, Dr. Henry.
Yep.
When we were doing is this different than like the quantum numbers? Because Jess was saying like when you do your quantum numbers, you do each level first and then you go back for like the Hund's rule. Is that the same or is it different?
No, it's the same concept. So what she basically means is that you're doing each level first, right? So you do this level, then you do the next level, and then you go through and you fill in this first. You don't have these 2 guys in the same orbital. So like this guy is representing just 1s orbital, the 2s orbital. This guy is it's going to be your 2p minus 1. This guy represents 2p 0. And this guy is going to be your 2p 1.
Wait, I'm confused. Hold on. So I remember Jessica said that we first draw the the arrows that are going up.
Mhm.
Yeah, and then you go back.
And then we go back and draw the
Yep.
arrows going down. Because
Yes, but you want to do that in the context of each of the different energy levels. You always want to start from the lowest energy level. So you draw the arrow going up, and then you draw the arrow going down because the 1s only holds 2 electrons, right? Then you go up to the next energy level. You have to go in order of energy levels. Do you guys understand?
no.
Okay. So
let me show you what let me annotate so you can see what we're
Yeah.
talking about.
yes,
Just because we're assuming that we're finding ms, which is the spin, and she said that if you don't do it that way, it's going to throw off your not your spacing,
So basically what
determining, yeah.
well, basically she said just go up and then keep going and then keep going and then keep going. And then she said
Go back.
we would go back again. So then
Yeah.
we would go back and go back, and then we would have our
yes, but she's saying that in the context because that's in the context of each of the different energy levels, right? So remember, when you have it, you have 2s, you have 1s, you have 2s, you have 2p. So in the case of carbon, we first put that first one up, then we put that next one up, right? In the case of carbon. If we're talking about, let's say, oxygen, right? Oxygen has how many electrons?
8.
16.
Oh wait, yeah.
I don't know.
Oh,
I
8.
just woke up, so I don't know if that's right.
it has 8.
8.
It has 8, right?
Yeah.
It's like, where are you getting 16, right? Because it's the same number of protons that you have. So in that case, if we're doing oxygen, so this would be carbon. So if we're doing oxygen, so we first, again, let me go through this. Let me clear, and then I'll explain it. So if we're doing oxygen, we're doing oxygen. That very first electron is going to go in the 1s, because the 1s is the lowest energy level.
Right.
The next electron is going to be going in the opposite direction, and you're going to fill that energy level first. That energy level gets filled first, then we go up to the 2s. Then we go up to the 2p. So we have 1, 2, 3. And then we come back and fill that other one. That's what Jessica was making reference to. But it's, you start from the bottom and work your way up. Understand?
Yeah.
Okay.
Okay, so like, it's kind of like there are 2 seats here, right? Now, this guy has to be filled before you can get to the next seat. Then this guy has to be filled before you can get to the next seat. And the way that you fill this is kind of like, they're kind of like guys in the movie theater. Guys don't like to sit next to each other in the movie theater, right? For some reason, right? So then they'll put a space between. But until they have to sit next to each other, then they will do that. So then they'll come back and, okay, so now I can sit here in the opposite direction. You understand?
That okay, yeah. So then so basically for Hund's rule, we have to fill up the first seats and then move on.
That's right. And remember, each orbital can only hold 2 electrons. So this guy can only hold 2 electrons, right? Then we have to move up to the next energy level. You don't want to go up to the next energy level. You absolutely must go up to the next energy level. Do you understand? So
Yeah.
you don't understand? So this, okay, so this represents the energy level, right? So when you're filling up electrons, you're going to go from the lowest energy level because you're lazy. You don't want to use a lot of energy. So you want to fill up these guys first. So you have your electrons filling these guys up first. So that's your first electron goes into this spot. Your next one goes into this spot. Then you go to here, right? So you have 8 electrons. Each electron has to fill up a seat. So you start at the lowest level, 1s, then your 2s, then you fill up your 2s, then you fill up your 2p if you need to fill up your 2p. Do you guys, are you getting it now?
Yeah, I understand it.
Okay. So, but when you're getting to that 2p, because 2p has 3 orbitals in it, right? So you want to make sure that you have 1 electron in each orbital before you go back and start putting another electron in with that other, because they don't want to be next to each other. They don't have to.
Okay. Yeah.
Cassie, you have that look.
Huh? Me?
Yeah.
No, it makes sense now. So ultimately, each energy level has 1 seat. You have to fill the seats first.
That's right.
So the P energy level has a row of 3 seats that need to be filled first.
That's
And then
right.
3D has a row that you would have to fill before going back and continuing.
That's right. That is exactly
Yeah.
right. Okay. So let's say we're talking about this very specific electron right here. Okay. So we want the quantum number for that electron. So what is the N?
2.
2.
What is the L?
0.
What is the ML?
Just 0.
And what is the MS?
Negative 1/2.
Negative.
Because it's going down.
Okay. So what about this electron here?
Two. And then 1 for L. And then for ML would be -1 to 1.
Would it be -1 to 1, or would it be
Or
just,
negative, wait.
so this guy would be your -1. This guy would be your 0.
Oh,
and
okay,
this guy would
gotcha,
be 1.
gotcha.
Right.
So -1.
And then our MS.
-1/2.
Okay.
So your ML is not your range, right?
What was that? Yeah, the ML is not the range. It's a specific number. So
Right.
it's either
Okay.
going to be that -1, maybe that 0, or -1. We're just letting you know that it's limited by the range.
Okay.
Yeah.
So what about this guy?
2 for N. And then 1 for L. And then 1.
1/2.
Okay. Okay, questions, concerns, Cash? And so we know that each of these electrons have a very unique set of quantum numbers. None of them will be exactly the same, right?
Right.
Okay, for this atom, okay? Piece of cake?
Yeah.
Okay, here.
Wait, Dr. Henry, I have a question.
Yep.
So last lecture you said that you fill in the 4s before the 3D, right?
Yep.
Why is that? Or why? This is the
Because
Because
question.
it's a lower energy level.
Because it has a lower energy level, right? So the 3D actually, 4s has a lower energy level than the 3D. And it's slightly lower than it, but because it's lower than it, we fill that in first before we do the 3D. Okay, even though the 3D is in another shell, you have some overlap between that orbital and that 4 where the 4 would start, and it happens just to be in a lower energy state than the other. Are you there, Selena? Do you get it?
Oh, I have another question.
Okay.
So if you had like an ion, for instance, do you take
Mhm.
electrons from the 3D or the 4s?
Yep. Then in that case, because it's always taken from the highest numerical energy level, even though that the energy level for the 3D is higher, technically higher than it, but the 4 is outside. You understand?
Could you rephrase it?
So let me see. So if we look at the energy levels, right? So here, this is the 3D. The 3D and the 4S kind of overlap, but the 4S is a higher number. So it's a higher shell than, or I should say, a higher level than the 3D. But energy-wise, if we look at specifically at the energy, it's lower. 3D is higher than 4. But if we look at level, 4, because it's 4, is greater than 3, right?
Right.
So 4 is greater than 3. Is that true?
Yes.
Okay. So since 4 is greater than 3, you always want to take from the one that is the highest level, which is 4.
Okay.
Okay. Now, so what does that mean, right? So that basically means that even though that the 3D is higher than the 4S, we're going to remove from the 4 first because of its location. It'll be easiest because the attraction part of it, it'll be easier for us to remove from the 4th level than going across and getting to that 3rd level, even though 3rd level is higher in energy.
Okay. So you will take electrons from the highest level.
That's right.
Okay.
You take from the highest level first. So when you're making ions, yes. Okay. Does that, you kind of get that?
Yeah.
Okay. Clear. Let's see. Okay. So on my screen, I would like you guys to draw the draw the electron configuration for, let's see, let's do manganese. Okay. Who's going to be my volunteer?
I can do it.
Okay. And then, since you're going to draw it, then I'll have Cassie. I want you to identify. Let's see. Let's do, it'd be N3. N3. L2. ML -1. MS 1/2. Abby,
Yes.
so you have
No.
in 3 L1 ML1 MS 1/2 Selena I'm going to give you N 2 L 0 ML 0 and MS minus 1/2. Okay, so all you have to do is circle the one that you have to find. And we'll give one to Kayla since she did the hard work. We're going to make her work twice. Whoops, if I could spell your name. It's one of those days. Well, actually, it's been one of those weeks. And I couldn't do math yesterday at all. My head was not working. Okay.
So all we're doing is circling the one that we're in charge of.
Yep. That's all you're doing.
Oh my, okay.
Oh damn.
Yep.
I covered the other.
Dr. Henry?
Yep.
Are you going to go over Z effective? Because that comes
I
up
am.
with Chem 101.
Yep. I'm going to go over it.
Okay.
Okay, I think I'm wrong.
Which one is yours, Abby?
The one next to Cassie.
The one next to Cassie? Okay.
Yeah. Hold on.
So
hold
let's see. So let's see. So Abby has, so it's 3, and so it's the third energy level. It's
Mhm.
L1. What does L1 represent?
P.
It's the P. So then it would be 3P, and then it would be 1. So that would be, this is -1, this is 0,
And then 1.
this is 1. So then, and it's also a positive value.
Yes.
So then it would be,
That one. Wait. So even though it has a negative pair at the, like, even though it has like an arrow going down next to it, it can still be 1/2, like a positive 1/2.
You're looking at that specific electron.
yes.
Oh, okay.
Remember
Yeah.
how Jess said you look at the specific, like your number of electron.
Yeah. Okay, never mind. Thank you.
Okay.
Yeah.
Okay. Questions, concerns, Cash? Good. So pretty simple, right? Not too hard
Mm-hmm.
For now.
for now. Okay, so let's move on. Maybe. Come on, clear. Okay. Okay, so then the off-Bach principle. And off-Bach basically means to build. And so in that context, the principle basically says that we want to make sure that we're determining the number of electrons that are equal to the number of the atomic number, right? Because it's a balanced situation unless it's an ion. So our number of electrons are going to equal our number of our number of electrons are going to equal our number of protons. And we always want to start from the lowest available energy level, and then we're going to be adding, we're going to be building from there. And we always have to keep in mind that we are going to use the Pauli exclusion principle, which basically says that you can't have like 3 electrons in the s orbital because it can only hold 2, right? So the most you could have is 2. The least you could have is 0, right? According to the Pauli exclusion principle. Yeah? Yes, no, maybe?
Yeah.
Okay. So here's our periodic table. This basically lets us know. So we know that this here represents our 1s region because we've talked about this before, I believe. Oh, well, if you're in 2A, you talked about it with me. So this is going to be our S.
Yeah.
This is going to be our P.
D is yellow.
Yep. This is going to be D.
Green is F.
And this is going to be our S. Now, on your periodic table, these guys here, they're often written down here. So these guys are part of the d orbital, and often people will make that mistake and not put them there. Do you understand? They're not part of the F. So if you look on P table, which I'll put up right now, maybe, if it lets me. Can you see my P table?
Yes.
So these guys really belong here. They're part of, these guys are part of the D. These guys are part of the F. And it actually has on here. So those guys here those guys really belong to the F. These guys are part of the D. Okay? Questions, concerns, Cash? So I think I'll add something to your sheets. I'm going to give you guys the long version. I'm going to make a PDF of it. Let me see if I can get it. Not this one. Come on. Where is the long version? Did they remove it? Let me see if they have it here. Give me 1 second. They used to have a wide version. That was available as well. Okay, so I'll have to get the wide version again. So the wide version actually gives you the order, so it's clear which way it goes. Okay, so the thing that we want to keep in mind when we're looking at this, and we always want to remember, is that after we go to the 4S, this actually is the 3D, right? And then after we go to the 6S, we go down to the 4F. Okay, so you go 6S, 4F, and then 5D. Are you with me?
Yeah.
Okay. So let me go back here. Oops. So old school, this is the old school way of doing it. That's actually taking into account every single configuration that exists, right? And so taking it where every single electron exists and exactly where they're located. And this actually gives you the nice energy levels and everything like that. So you always fill up from the bottom working up. So it's always the 1S, the 2S, the 2P, the 3S, the 3P, the 4S, the 3D, the 4P, the 5S, the 5S, the 4D, the 5P, the 6S, the 4F, the 5D, the 6P, and onward, right? So if we look at our periodic table, it follows that order. Okay? Questions? Concerns? Cash?
You're offering? Okay.
Don't get happy now. Okay. Okay, and the other thing that we want to sit there establish is, because we want to use their electron configurations to understand which electrons are going to be valent or are going to be able to be used for reactions and stuff like that. And that's kind of important too. And that's also part of the reason why we do the electron configuration. Okay, so let me give you guys some insight. Remember, I told you there are some exceptions to the rule in terms of your electron configuration.
Yeah.
Mm-hmm.
Okay, so let's talk about some of those exceptions and the way that you would determine those exceptions. So chromium is an example of one of those exceptions. Okay, so the way chromium works is, so when we write, so let's go ahead and do what we would think chromium to be just based upon the periodic table, and then we'll make the adjustment with the exception. So if we're writing the electron configuration, we write it 1s, 2, 2s, 2, 2p, 6. And you guys went over this with Jessica. I'm making sure that I'm not reteaching stuff, because I'm just assuming that you guys did.
She went over it briefly just because some of us had forgotten as like a refresher for us. But yeah.
Okay. So 1s2, that's a 2 here. So 2p6, so that's 1s, that's 2s, that's 2p, that's 3s, 2, that's 3p6, and then that's 4s, 2, and then it is 1, 2, 3, 4, 3d4. Okay, so by looking at just the periodic table, this is what we would get for our electron configuration, right? Now, what really happens is, because you have this kind of blurred line between the 4s and the 3d, they're really close in energy levels. 4s is just slightly bigger. So there are certain circumstances that will cause the 4 to get pushed up, or an electron to go into, not the 4 to get pushed, the one that's in the 4s to get pushed up into the 3d. And the reason why it does that is because if you have 1, 2, 3, 4, 5. So this is the 3d, right? And if we had drawn this out, we'd have 1 electron here, 1 electron here, 1 electron here, and 1 electron here, right? And so this guy is unoccupied. Now, if it's really close to being 5, it's going to want to put an electron there. So the one that's in the 4s, so this is the 4s, actually causes it to lower its energy level if this guy is off. So it'll just take that one that would normally be here, this guy, and move it here. Okay. So the way that you determine that is, if you take a look at these numbers right here, can you guys see those really, really, really small numbers? Let me see if I can blow this up
Kind of, yeah.
a little bit bigger. Okay, so we're looking at chromium. So this tells me I have 2 electrons in the first energy level. I have 8 electrons in the second energy level. I have 13 electrons in the third energy level. So if I did 13 electrons, so that means that I have, so that's for the third energy level is 3s. So there'll be 2. 3p would be 8. Would be 6. And then 3d would be whatever's left. So that's 8 minus 13, which should be 5, right? So I did my math right. So that's the number that we have in the first energy level. This is the number that we have in the second energy level. This is the number that we have in the third energy level. And then this is the number that we have in the fourth energy level. So then that means it will be 4s1. Okay. So then it would be, to get everything written down, so it'd be 2s2, 2p6, and our 1s2. Okay. Do you see that?
Yeah.
Mm-hmm.
Okay. So if we're talking about valence electrons, what electrons would be valent in this regard?
The highest energy level.
The highest energy level. Right. So that 1s, and actually it would be, in this case, because this guy isn't completely full, so it would be these guys, and then you'd have these guys as your valence. So we'd use these guys. We could write this as, what is that? What is the noble gas? Did you guys talk about the noble gas abbreviations?
Yeah, so it would be AR.
Okay, so then we'd represent this guy as AR. And then you just have to write, oops, my handwriting, gosh, I'm on a roll today.
At least you could do math though.
Yes, barely. Okay, piece of cake?
Mm-hmm.
Okay. Okay. Oops. Okay, let me clear this.
Stop it. Stop.
Oops. Okay, so you guys understand how we went from our quantum numbers to our electron configuration, right?
Yeah.
Okay, so this is just basically showing you the full diagram and the spin and all of that stuff for each of the ones, okay? So we've talked about what we call our valence, right? Our valence electrons are the ones that are not in that core. So we have the core that basically are going to be represented by those noble gas. So we can use the noble gas to sit there and make up our core. And in that case, you guys use argon. Argon would be the core, and then the electrons that are extra that are available for interacting would be the valence electrons. So, and they're the electrons that are in the outermost shells. Okay. So here for sodium, this here represents our core. So we would abbreviate this as Ne, and then we'd have one valence electron.
So are your valence electrons like when you're doing your setup, are those your paramagnetic ones?
Okay, so when we talk about paramagnetic basically means pairing, right? So paramagnetic deals when we're interacting with another atom, when we're forming a bond.
I thought that was diamagnetic because there was two.
Yes, but paramagnetic also deals with that. So
okay.
Paramagnetic basically means that you don't have a connecting, you have free electrons available, you know, and so they don't have a mate that's going to balance them out. Okay, you get what I'm saying?
Yeah.
Okay, we'll talk. I promise you, we will talk about paramagnetic and diamagnetic here when we start talking about bonding.
So ultimately, your valence electrons is just the outermost shell that you have when your highest energy level.
That is correct.
Okay.
Okay. Okay. Questions, concerns, Cash?
Nope.
Okay. So let's see. So these are some examples of the different electron configurations. So, and this is using the abbreviation form. And we use the abbreviation form so we don't have to write out all of the lower ones. Okay. So let's see. Can you guys do me a favor and write out the electron configuration for let's do the electron configuration for germanium and easy ones.
You want the long version?
I want the short version.
I could do it.
Okay,
And then I
right.
got
Write it on my board.
You said germanium?
Germanium. Yep.
I'll try right here, I guess. Can we do both of them?
Actually, someone else do nitrogen.
Okay.
Any volunteers?
Yeah, I can do it. Mhm.
No. I'm still waiting. It's behind my screen. Okay, piece of cake.
Yeah.
Oops. Okay.
What, Dr. Henry, what's it called when it's, do you just state the short version versus the long version? I can't remember if there was a specific name.
The long version basically uses a core, right? And so in that case, you're looking at valence electrons. So it allows you to look at how many valence electrons you have. So like for instance, here, how many valence electrons do you have? For germanium. And normally you'd always want to tell me what element you're working with. I'm going to put your GE here so I know that.
Okay.
And then nitrogen.
So then would it be 14?
Right. Yep. So you'd have 14 valence electrons to work with. Right.
Okay.
Primarily the ones that you're going to be working with are in the p orbital, right? So those are the ones that are freely available because these guys are already occupied. These guys are freely available. But in theory, you have all 14 to work with.
But you just state the, again, long version versus short version, because Jessica, I was like, isn't there a shorter way to do this? It's because we wrote the whole entire electron configuration out.
Yeah. So yeah, this would be the short version.
And it's
right?
just short version, right? There's no, okay.
So, or you say the one with a core.
Oh, okay,
Right.
gotcha, okay.
So that's a core. Okay, questions, concerns, Cash? Okay. Clear. Clear. Okay. Okay, so we've talked about the f orbital and then that little quirkiness of the f orbital, right?
Mm-hmm.
So where it's actually one is the D and the other one is the actually F. Okay, so let's see. Okay, we've also talked about the exceptions, right? So we remember what we're expecting and what we actually have. So part of that is because we want it to be half full or completely full, right? When we get to the d orbital, it wants to be either half full or completely full. So in the case of copper is, if we wrote it out, it would be argon 4s2, 3d9, right? So, but since this is 9, we want to try to get that d full if we can get it full. So it'll actually borrow that electron from that s orbital and pop it up into the d orbital. Are you with me?
Mm-hmm.
And so do you guys see the distinction between the two?
Yeah.
Selena?
Yes.
Okay, good. Oops, sorry. Okay. So when we talk about, let's say, palladium, right? And we're talking about its valence electrons, it's going to use that 4s first, right? The higher energy level first. The 3D is completely full. So that's considered to be, it's going to count if it's a core since it is completely full. Do you guys understand what I'm saying there? Or is it kind of weird?
I think so, yeah.
Yeah. So in theory, right, we know that the 3D is full. It's completely full because it holds 10 electrons. There are 10 electrons here, so it's completely full. So the ones that you have to work with is just that the outer layer, that outer level. So if we're going to be taking from anything, we're going to take away from that outer level. We're not going to take away from that 3D because that's in that inner core. So it's not considered to be valence. These guys are considered to be valence. Okay?
Yeah.
Let's see, clear. Okay, so if we have Vendanium, right? Vendanium has 5 valence electrons, right? Because the 4s, the 4 level isn't completely full, and the 3 level isn't completely full. So here we have 5 electrons to work with in terms of its valency. Are you with me?
Mm-hmm.
Okay. So in the case of Promethium, PM, which is in the F, its the last electron is in the F orbital. Well, the F orbital isn't completely full. And the S, the 6, I'm sorry, the 4, the 4F isn't completely full, and the 6 isn't completely full. So in this case, we have a total of 7 valence electrons to work with. Okay, so do you see the distinction between when we're talking about the 3D here, where the 3D is considered to be completely full? So then that's part of our core. It's considered to be part of the core. and you only had 3 valence electrons to work with, compared to here, we have 7 valence electrons to work with. Because neither of these, well, this is the outer shell, and this guy, that inner part isn't completely full. Okay? Are you with me, Selena?
I'm trying to process it. My brain's really slow in the morning.
Yeah, that's right. You don't drink coffee, so you don't get that jump.
Sometimes.
Yeah.
Wait, why would argon be the core electron or the core gas?
For this guy? So
Yeah.
let's go. Let's take a look. Okay, so we're talking about PM, right?
Mm-hmm.
So PM is actually in this. It shouldn't be argon. Actually, that's a mistake.
Okay.
It should be
That's why I was
XD.
confused.
Yeah.
So it'd
XD
be
should there.
krypton.
Yeah.
Or yeah.
No, xenon. It should be xenon.
Oh, xenon. Yeah. Okay. Thanks.
So let me fix that in my notes. So that is a typo. Maybe. Let me find my notes. Let's get and it just closed out on me. Oh no, it didn't. So that should be good eye. Okay, let's see. Let me save that. Come on. Sorry, computer's running slow. Okay, clear. Okay, so when we start removing electrons or adding electrons, then we start getting into the formation of our ions. So we have the cation, which is a positively charged ion. So are we removing electrons, or are we, if it's positively charged, is it going to be removing electrons, or is it going to be gaining electrons? Or adding? Removing. Okay. So let's see. So anions are the opposite. And that one is actually gaining electrons. So can you guys do the electron configuration based upon that, right? So remember, in the case of removing electrons, if we're removing electrons to make the ion, it's going to make it positively charged, the cation. So what is going to be the electron configuration? And where are you going to remove from in that case? So what would be for sodium? What would be the electron configuration for sodium generally?
Should I write it?
Yep.
Okay. And that would be it normally.
Okay.
Wouldn't it
Yep.
just go to, it would go to just, 3s1 wouldn't be a thing. It would just be 2p6, right?
That's right. We'd end up on 2p6. So it would just be, we'll get rid of this guy. So we're removing that one electron. So then this would be our electron. Okay. So when we add electrons, we just add towards the end. So if we have p, 3 minus. So what would be the electron configuration for that? Abby. We'll have Abby do this. And then Selena. And then Cassie.
Okay.
Oh, you're driving. Okay. So then, Cassie, you get a pass this time.
Okay, sorry.
So then we'll have Abby and Selena.
Did you put my name with a K?
I know I did. I wasn't thinking.
Dr. Henry.
Okay, so I'll do P3 negative first.
Dr. Henry, do I write like the whole thing or can I write it with the core?
You can write it with the core.
Okay.
Yeah.
I need to annotate.
Okay. Okay. Good, good, good. Okay, so real quick, we're going to talk about, we're going to kind of skip a little bit and talk about Z effective. Since you guys need this to finish up. Is that correct?
Yeah.
Okay, Z effective is going to be equal to Z minus S, where S represents like the shielding electrons. And the shielding electrons are basically, it's the total, if I could spell, total electrons, TOA, minus the valence electrons. Okay, so if we have neon, and Z represents the atomic number, okay? So if we have neon, if we're calculating Z effective, then it would be, so Z effective for neon, how many total valence electrons? I mean, what is the, sorry, the number of, what is the atomic number for neon?
Be 10, right?
Okay, so we have 10. Okay, and then we want the total number of electrons. How many total electrons does it have?
10.
10 minus the number of valence electrons. So here, since it is a noble gas, you assume that all of those electrons, even though it's full, right, those are still going to be considered the valence electrons. So in that case, it would be 8. So 10 minus 8 is what?
2.
So your S is equal to 2. So then we'll put 2 here. And so then this would be plus 8. So our total effective would be plus 8. Okay.
Okay.
So if we have sodium, let's say sodium alone, and then we'll do sodium ion. So what is our Z effective for sodium? For Na.
It'd be 11.
Okay. So it's 11. How many valence electrons does sodium have?
2 or 1.
So it's 11 minus, so we'd have total electrons is 11 minus, the number of valence electron would be 1. So then that's minus 10. So in that case, it would be 1. Okay. So if I have sodium plus, what is my Z effective? So in that case, I've gotten rid of that 1 valence electron. So
10.
So this guy would be, so it would be 11 still, minus, so our total number of electrons is 10, minus number of valence electrons. In that case, it would just be that 8, right? Because then you're assuming it's like neon in that case, so it would be 8, so then that equals 2. So 11 minus 2. So the effective, Z effective would be 9. You guys get that?
Yeah, I think I get the basics of it. So
Okay. And so what that basically means, the Z effective basically lets us know that it gives us an idea what is going to be the pull that is going to be exerted on a specific electron by the nucleus. Okay, so that's what it represents. Questions? No questions? Okay.
Wait, Dr. Henry?
Yep.
I need a refresh on something. So,
Okay.
so for the ions, so
Yep.
like SM, for instance,
Mhm.
you're taking the electrons, you start with the highest level, so like the 6s, not the 4f.
Yep. So yeah, so
Oh,
that is correct.
Uh,
You made a mistake there.
yeah.
That's your own mistake. So it should be 4. And then that guy. It's gone.
Okay. But if they were both, like, let's say it was 6s2 and 6p3, for instance,
Uh-huh.
you would take electrons from the one with the highest subshell?
The highest number, yep. Whatever the highest number is. You always go from that highest number. 6 is higher than 4, so you take away from 6. So if you had 4 and 3, so then you would take away from the 4 instead of the 3.
Okay.
Yeah. Okay, questions? Okay, so we're gonna have to stop here. If you guys have any other questions, I'll see you guys in my office hours.
Wait, do we have lab to do?
So,
Physical lab.
so you're not gonna do a physical lab, just go ahead and do the simulations. Do both of the simulations. Technically, you should have a physical lab, but I'm still in the process of putting the information.
Okay. For the
I have to
simulations,
modify the lab. What was that?
okay. For
Yeah.
for both simulations, you're gonna fix the IT thing, right?
I am. I'm gonna fix the IT. So hopefully I'll try to get that done right now, since I have the same problem I'm gonna have with another class too. If that's not working for you, it's not gonna work for my other class either. So I'll have to get that fixed.
I have a quick question. Also, both homework assignments are gonna be due tomorrow, right?
Both homework assignments will be due, yes.
Okay.
Oh, no. You only have one homework assignment that's gonna be due tomorrow.
Oh, because it's
And that-
saying that we have one due tomorrow at 2:18 and then one due tomorrow at midnight.
Okay, so only the one that's gonna be due tomorrow at midnight. The other one is gonna be pushed back because you haven't done it yet. We haven't talked about it. So I'll fix that.
Okay.
Okay, thank you for letting me know.
You're welcome.
Okay, I will let you guys go because I have another class. I will see you guys maybe in my office hours,
Yeah.
or if not, next week. Have a good day.